Um, so if you remember last time, I was talking about was essentially this idea of Wasserstein distances. Just for a reminder, I mentioned the fact that there were two types of problems usually in optimal transport. One that is favored by mathematicians, the like densities, and this is called the Morse problem. Maybe you remember this integral was this idea that you were taking mass at some point x, bringing it at some point t of x, and overall you wanted to recreate a different shape of sand. And then I mentioned this Kantorovich relaxation, which was this idea that actually we could also see all of this as a joint probability distribution that we're trying to find that assigns the mass of that's available in some measure, maybe in a variety of other points, and eventually we get what we want, which is a second measure. So the point of interest, the variable of interest now is joint couplings with prescribed marginals mu and nu. And then, if you remember, I did a bit of math and explained something called Kantorovich duality, which helps you maybe connect these formulas to another formula that maybe you're familiar with, which was this idea that Wasserstein one distance, which is the case where this cost function here is just a distance, is this integral probability metric that Arthur discussed a lot. And then I said, well, this distance has some nice properties, which is that it seems to somewhat agree a bit with what our intuition would be in terms of how to mix two probability distributions. So I try to convince you with this example that something different is definitely going on in the way we average things in optimal transport with respect to the way we average them in the traditional Euclidean way. Then to illustrate a bit more that, I try to give you some visual eye candy, in 3D to show that something was happening there. And then I close my lecture saying, well, in many of those applications, especially the interpolations, maybe I'm not explicitly making this explicit in math, but what's going on is we're not only trying to compute optimal transport, we're not just trying to see how far two probability distributions are, but what I'm trying to do in some of those applications, and in many of the applications that have been discussed, such as GANs, and I will explain a few more, what is also at stake is not only to compute the distance itself, but how can we actually differentiate it in its arguments. So again, I will make the easy parallel to the Euclidean distance that we use in all our applications. Well, Euclidean distances help us consider how far two things are, but we also use them a lot to compute gradients, right? We measure how far something is from a target, and then we try to compute the gradient of what makes us closer to that target. And the reason we like the squared Euclidean distance is because computations are easier. What would happen if we were to do this in Wasserstein sense? So imagine that I have a target probability distribution that I want to look like. That might be the target distribution of my natural images. And then I am producing images, and I want them to be closer overall to this manifold of data. So this is there must be some answer to do this computationally. We can't just say the Wasserstein distance is great. Now, on the computational side, just do what you can. So what I will be talking about from now on is basically how to compute this idea of optimal transport. And what I will provide you with is a few situations where this is easy. It's easy to compute this optimal transport distance between distributions. And those easy solutions are actually favored by statisticians. They are in themselves solutions that have been used in different communities. So you will see that this Fresche inception distance that people have been using is actually a Wasserstein 2 distance for Gaussians. And then I will try to go into a more general setting where we actually consider not only probability distributions are not necessarily Gaussians, but more complicated, and then to things that are probability measures that are discrete versus continuous, or continuous versus continuous. So this brings me to, I guess, the current typology of people try to compute in optimal transport. So unlike, for instance, the Kullback-Leibler divergence or other F divergences, and I hope I have convinced you of this, we don't really need to make a lot of assumptions about the continuity of the densities or whether one blows up when the other is equal to 0 or things like that. In optimal transport, everything is always well defined as long as you take the Kantorovich perspective. So as long as you optimize over couplings, you're fine. And remember why? It's because no matter what probability distribution you give me, pair of the probability distributions you give me, I can always come up with one coupling that has those two marginals, and that's the independent coupling, the one we mentioned about. If the first marginal is mu and the second marginal is nu, then the coupling will be mu of x times mu of y, basically. And this works, this has good marginals. So there's always a way to couple a discrete measure with a discrete measure, a discrete measure with a continuous measure, or a continuous measure with a continuous measure. Now, there are three cases that people like to study in particular. Those are the discrete to discrete case. So this is a cloud of point and a cloud of point. A cloud of point to a probability distribution, and a continuous distribution to a continuous distribution. And to simplify the argument, basically the one that's on the top left is, as you would expect, the one that's been the most explored computationally, because it's very well posed, it's simple. We can try to, we have the entire access to the entire information. And in that case, well, there's been a lot of work. So I will show you that the most basic formulation of this Wasserstein distances for two cloud of points boils down to a linear program. And linear programming has been here for a while, right? Now, I will also show some faster methods that have helped quite a lot in recent years, which are based on regularization. Then there is a second class of problem, this discrete to continuous problem. So this is of a lot of interest in applications in graphics. There's also a lot of industrial applications, like to design reflectors for your cars, for instance. So optimal transport is there when car companies design reflectors so that your lights illuminate exactly the proper areas that you want to be illuminated while you're driving. So typically, if you're driving on the left, as we do here, then you don't want the light of your beams, your light beams, to go too much to the right to lighten up the car that's driving in front of you. So you rather prefer to have something that's focused on the left area. And this is an optimal transport problem, and there's a lot of industrial applications that basically stem from those ideas here of the semi-discrete case. I will not talk too much about this, but there is another case which I hope you can see some relevance for, which is the GAN case. In the GAN case, typically you have access to a manifold of data which is given to you. It's maybe 1 million images. And you have this push-forward distribution, you remember, that takes your latent space and you use your deconvolution network and you create this manifold. And then you could imagine, is there a way to have a good computation to say that this is how far this is from this and how can I make it closer? And then there's the continuous to continuous case, which is an even more sophisticated one, which is well understood in the context of, I would say, physics, fluid dynamics. And this is something that's been going on for about 20 or 30 years. And in that case, this is I would say, the realm of PDEs. So people in analysis try to solve this kind of problems, but they do so usually in low dimensions, hence something that's not very useful for us, right? We are more often interested in higher dimensions. So for each of those, there are different communities, I would say, and but I will be focusing mostly on this in this regime, the discrete to discrete. Now, let me start with the first cases that some of you might be aware of, and for which there's no computation issue to speak of. The discussion is closed. So there's one which is very convenient and that statisticians are very familiar with. So if you talk about Wasserstein distances to statisticians, very often this is what they have in mind. And what they have in mind is distributions on the real line. So univariate distributions, okay? So I'm measuring just one random variable with one number, and then I'm trying to compute the Wasserstein distance between them. So the nice thing is the following. If the cost function that you are considering on the real line, so the cost between two numbers, is translation invariant, and it's a convex function of that difference, of the absolute value of that difference, then everything is very easy, and the entire idea of Wasserstein for the real line is basically just look at the quantile functions. So what is a quantile function? It's the inverse of the CDF, of the cumulative density function. And if you have access to the quantile functions, basically computing the Wasserstein distance between the two densities or probability distributions, even if they are discrete, you would need to take an inverse generalized quantile function. Then it's basically integrating the quantile of the first measure minus the quantile of the second measure at the same level with this C function between 0 and 1. Okay, so that's so let me just try to illustrate this. Imagine I have this distribution, I have this other distribution, and I'm going to, let's say, consider a cost between two numbers, which would be anything that depends on their difference, the absolute value of their difference. So the first thing I do is I plot the CDF of the first distribution. Remember, the first distribution had 2 bumps. You somewhat see them here, and the other one had 3 bumps. You see them a bit here. So what is a quantile function? It's just the inverse of those 2 curves. So what is the inverse? It's just you would basically take the symmetric along this 45 degrees direction, and then you get the plot of the 2 quantile functions. Now, Wasserstein is just as dumb as compare those 2 curves with any cost that you want that is just a function of this difference. So it will be integrating the difference. So this is basically the quantile function at x for this, for the first measure, quantile function at x for the second measure. You have this, the stick, you know, has this certain length. And then you take a function c of that. So that might be the square, for instance, if you're taking square Euclidean distance, okay? So you would integrate the square of the length of those sticks. So there's one case where actually integrating the length of those sticks is the same as integrating the length of those sticks, and that would be when C is just the identity. When basically you use the Wasserstein 1, okay? So the Wasserstein 1 distance on the real line is also, just because integrating in this direction or this direction, the length, only the length is the same, it would be the total variation distance between the CDFs, okay? So it's a tool that has been used a lot in testing theory. So Wasserstein 1 is, again, you narrow down, it's kind of an intersection of many things. It's difference between quantile functions, difference between CDFs. If you take the cost to be squared, then it's no longer true, and the proper representation for this is the quantile function representation. So let me just say as a side comment, you remember these curves that I just showed earlier, right? Sorry, it's this one. So you have a probability distribution, another probability distribution. I'm averaging them in the Euclidean way, like this, elevator-like, and then I'm averaging them in the transport way. So here is how you can actually get these curves in the middle directly. The only thing you do is you compute the quantile function of this blue curve, the quantile function of this red curve, and then you play this elevator game where you take the sum of the two, or you interpolate linearly between them, and then you go back to the density that corresponds to this interpolation of the quantile functions. Okay? So you would take, in this particular curve here, it would be just like summing this, let's say 1/2 of this plus 1/2 of this, you get a curve that's somewhere in the middle, and then you take the density corresponding to that quantile function to get the average. Yeah? No, actually okay, very good question. It would be valid for Wasserstein 2 in this case. The reason being, when you take a distance as a squared Euclidean distance, interpolation is linear. If you take, for instance, if what you call a mean of two things is the point that is the closest to those 2 points, okay, then the fact that it's just the term of the two is applies only for the Euclidean distance. So it might be something a bit more complicated. If it were to be Wasserstein 1, that's a good question. I guess in Wasserstein 1 it's not very well posed. My intuition is that it's not so well defined, because if you think about what happens when you take a point between a segment, basically the distance is constant. The sum of this distance to this point and this plus this is always constant. So any point in between is somewhat a mean in the distance sense. And if you only take as a constant distance. If you take squared Euclidean distance, there is only one point that is the middle, and that's the lowest distance to the two, and that's the mean of them. So if I had a blackboard, it would be a bit easier to say all of this with a drawing. But so in the picture that I was, basically just to summarize, Wasserstein equals play with quantile functions. Okay, so everything you would spontaneously do, like average things, take a distance between things, is happening in the quantile function world. And actually, a lot of people have found that before thinking about optimal transport. There's a lot of normalization procedures that people have considered. So this idea of interpolating between two distributions in the optimal transport way, people were considering it already using quantile functions. So they were doing optimal transport without knowing it. Now, there is another case. I'm going to split the formula like this. It's a bit, the formula is a bit big, as usual when we play with positive definite matrices. But there is another case where things play out very well and very simply. And it's the case when you compare two Gaussian distributions. So suppose that I have one Gaussian distribution with a mean mu and sigma mu, it's a covariance matrix sigma mu, mu and sigma nu. Then, to transport optimally one Gaussian to another, I will give you the formula. There is a closed form formula. And we know that the distance, so this is the Wasserstein 2 to the square. So remember, Wasserstein 2 just means that the cost is a squared Euclidean distance. Then in that case, it's just the difference between the means plus some metric between covariance matrices. And that metric is called the Burr's metric, and it has this shape here. And I don't know if Sébastien gave the explicit formula for Fréchet, inception distance, but it's exactly this. Basically, I don't know why this was attributed to Fréchet. Other people, of course, can claim a bit of that name, but this is a distance between covariance matrices. And this distance between covariance matrices, so here I call it the Burr's metric. It's been discovered in information geometry, in quantum information, and many other fields. And it kind of makes, it has a lot of very nice geometric properties. So it's kind of intuitive. If you compare a Gaussian with a Gaussian, you compare the means, how far the means are, and then how far their covariance matrices are with respect to this. So the way you can prove this is actually, it's not very complicated. It doesn't play out very well on the screen, so I will not refrain from spending much time on this. But here is the deal. You have one probability distribution, one Gaussian and another Gaussian. So what we know, maybe I will do this first here. What we know is that when you have a Gaussian, a random variable that's Gaussian distributed, you take a linear, if you modify that random variable and take a linear map, apply a linear map on that random variable, so let's say x is m sigma, and y is c times x plus b, so be a vector, c a matrix, then you know that basically you still have a Gaussian, right? That's a fundamental principle in Gaussians. And what you will get is that you will get a Gaussian that's been moved a bit away using this addition of b, and then you also need to modify the first mean m, and then the covariance matrix also needs to change a bit using the information that the new transformation that you apply to your random variable c. So it turns out that, please leave this out. If I apply the map, x becomes the mean of the second Gaussian measure plus a times x minus the mean of the first measure, and a is this matrix, a bit horrible. Well, you can very easily see, if you just do the basic math, that this thing, basically, if the first variable x was Gaussian distributed with the first parameters, it will be Gaussian distributed with the second parameters after being applied this linear map. Why? Well, first you can see that a times x, you will have a and a transpose on both sides. This is the first sigma mu, and then everything cancels out magically, and then you only recover the covariance matrix of the second distribution. So I encourage you to, if you're interested in this, just do the computation by yourself at least once to convince yourself that this seemingly ugly matrix is actually exactly what you want. So the first thing that we get is that this map transforms the first distribution into the second distribution that we want. Now, there's something nice about this map, and it's not maybe directly obvious, but this map is actually the gradient of a convex function. Why? Because this matrix A here is obviously positive definite. You know, it's already symmetric, and I'm taking square roots, inverse square roots of positive definite matrices. And we know that this is positive definite, right? And so what happens is that I found a map which changes the first Gaussian into the second. And that map itself is a gradient of a convex function. So here is what this map looks like. This is the first Gaussian. This is the second Gaussian. using the parameters of this Gaussian and the second Gaussian, I can come up with this map A. Okay, map A is this thing here. And then I subtract the mean and I add it here. And then what it does, it essentially tells me, okay, this point is actually, this is like the Monge, if you want, set of instructions. This is what Monge would tell the worker. Every time you have something at x, bring it to ax minus mu plus mu nu. Okay? And then what you have here is a map that maps Gaussian to Gaussian. That's simple to check. But it's also the gradient of a convex function because of the positive definiteness of this function. And let me just represent that function. Here, if I define psi as this quadratic function, you can all convince yourselves that the gradient of this thing is my map, okay? And this is obviously a convex function because A is positive definite. So here is my function psi, okay? I have a function psi who is convex, whose gradient moves this measure to this one. So by Brognier theorem that I very briefly mentioned, it's optimal. It's necessarily optimal. So here you have a very short proof of why this Burr's metric has this closed form and why it's easy to evaluate. Let me just say that what this gives you is a nice way to interpolate between Gaussians. So if I have a Gaussian that's here, let mu 0, and a Gaussian that's here, then I can very easily have basically a linear interpolation of Gaussians, and it's pretty much what you would expect. It's some kind of interpolation, linear interpolation between the two positive definite matrices. So all of this is closed form, and it's easy to check. Now, I will briefly say that this not only applies for Gaussians, it also applies for something that's called a elliptically contoured distribution. So elliptically contoured distributions are basically densities or measures whose level sets are elliptic. So Gaussian is obviously fits the bill, but there is another case where this is also true, and it's uniform ellipsoids. So here I've represented, so here we are in R3, and I have represented ellipsoids, okay? There's the first ellipsoid A, which is kind of big and full. B is another one. So here I'm really considering the uniform distribution inside the ellipsoid. And a nice feature of this Wasserstein-Burr's metric that we call is that actually you can also compute the distance between this full ellipsoid and this segment, this ellipsoid and this ellipsoid on the plane, or this point. This point is also an ellipsoid. It's a degenerate ellipsoid with no randomness. And in fact, if you compute the values for those different ellipsoids, they are equidistant, meaning, sorry, this ellipsoid is at the same distance to this one as it is to this one, as it is to this one, as it is to this one. So you can very easily come up with so it's a nice geometric distance between things that are beyond even Gaussians and that can be degenerate a bit. Now, let's move on and try to tackle increasingly general problems. So not just Gaussians, not just univariate distributions. There's not that many examples where it's closed form, so I think I can get around the examples pretty quickly. There's another case where things actually are quite simple, and it's where you only compare two Dirac measures. So imagine I have a Dirac measure here, and I have a Dirac measure here there, and my cost is the distance. Well, the Wasserstein distance between the two Diracs is actually equal to the distance between the points. And so this seems like a trivial statement, but it's, if you look at all of the other definitions that you're familiar with, like the F divergences or Kullbach's Leiber, etc., this doesn't work, right? All of the measures of similarity that you get from information geometry don't give you this result. The fact that the distance between when everything is kind of concentrated at one point and at one point, those property distributions are as far away as their points are. Okay. Now, there is another case which I think you're all familiar with as well, which is this idea of optimal assignment or optimal matching, which is one of the elementary CS problems that we consider at university. So imagine that you have two clouds of points of the same size, and of each point has the same weight, the same influence. So we have 4 red points and 4 blue points here. And we want to compare them. Well, if you actually write down the math of this Wasserstein distance, even going from this continuous formulation, you will find something that is basically telling you, I need to find the optimal permutation or assignment which assigns one red point to any blue point. And one red point can only be married to a blue point. And there's no, once this red point has selected this blue point, no other red point can use it. Okay, so it's a one-to-one assignment. And so in that case, well, the Wasserstein distance between the 2 point clouds is exactly the same thing as the optimal assignment, optimal matching problem. Now, in a more general setting where we have maybe a blue measure and a red measure, which have a different number of points, different length of sticks. So there is one red measure which is characterized by weights, AIs, A1 to AN, X1 to XN, sorry. So the AIs are basically the lengths of those sticks, and the XIs are where those points are. And here we have BJ's length and YJ's points. And the sum of the AIs is equal to the sum of the BJ's, right? We're comparing things which have the same total mass. Then in that case, what is the problem? So when you see this, of course, I would like you to remember the counter-reach problem, such as I had defined it earlier. You know, this is the barracks, this is the front line. I need as many soldiers in the front line as I have in the barracks. What is the optimal way of sending them, right? Well, in that case, everything is really the way I had described it to you with these cartoons. I am going to first encode the geometry of my set of points in this matrix, which is the distance, the pairwise distance matrix. It holds all of the distance between xi's and yj's, eventually to the power p, if I'm using 2 Wasserstein, etc. And then, remember, Kantorovich problem, we have this network which gives us this geometry, the distances, and then we have all of those matrices that we can consider that have the right marginals. And so here I've written this in a slightly more compact way, which is all the matrices NM. So remember, N is the size of the first measure, maybe the size of how many barracks there are, and M is the size of how many frontline points I need to cover. And so it will be P of size NM, such that P times the vector of 1s is equal to A, and P transpose times the vector of 1 is equal to B. Okay, so it's just a conservation of mass constraint. Now the optimal transport problem, again, Kantorovich was the same thing, is the minimum of the dot product of this P matrix to the matrix of distances, pairwise distances. So let me just try to give, maybe I will skip the dual formulation because I may not be using it so much immediately. So let me just try to give you a geometric perspective of what's going on. How many of you here are familiar with linear programming? Can I ask? Okay, so it's a good share. Okay, so I think this kind of picture is not it's not new for you, definitely. So in linear programming, we typically represent the set of constraints as some polyhedron. Here it's bounded. It happens to be a bounded polyhedron, so it's polytope. So we have a set of matrices which sum to 1 have the right marginals, which are defined only by the weights of the first and the second measure. We have one matrix which is given to us, and it's the one that encodes the geometry. And then what we want to find is the matrix in this set that has the smallest dot product with this vector. So where would you expect it to be? Of course, anyone that has done the programming will remember this. The one point that has the lowest dot product with mxy here is this one, right? It's the one. Every time you slide a hyperplane that's orthogonal to this vector, you have matrices that have that share the same dot product, and then you want to go in the opposite direction as mxy to find the one that is there. So it happens to be at a corner here. It's always the case that there is a corner that has the smallest possible value. Sometimes you might have some facets which are optimal, but in this case here, it's well behaved and it's one point there. So the whole goal of linear programming, and those were advances by Danzig in the late 40s and other people, Fort Fulkerson in the 50s, to solve specifically this kind of optimal transport problem, is to get here. Okay, and there are lots of methods to do that. You have simplex type methods that essentially kind of go from one corner to the other. You have an algorithm that's called the auction algorithm that is more numerical but also does this job. You have interior point methods. You have a zoo of methods. And for about 30, 40 years, tremendous effort was put into trying to understand how fast we can get there. How fast can we approach this optimal transport matrix, or more generally, optimal network flow solution? And what the consensus is right now is that the best bounds that we have are of the order of n cubed log n, when n is basically the number of points. Let's say n is equal to m to simplify a bit the bound. So if you have about n and n points in both measures, the effort that you need to make to compute this optimal transport is n cubed log n. So if you're familiar with linear programming, here I'm describing a problem essentially whose size is n squared, right? We have a matrix that we're looking for. But I am telling you that with n cubed log n effort, you can get the solution. It's actually very, very fast for linear, as far as linear programming is concerned. The more general bounds for linear programming are of the order, if the dimension of your problem is n, then the bound would be n 3.5. Here, the dimension here being like n squared, I mean, the number of variables being n squared, that would be n to the 7. So here we have something that's actually extremely fast and extremely efficient if we compare it to other more general linear programs. However, if you think in terms of machine learning, of course, this sounds horrible, right? In cube, whenever something is in cube in machine learning, then you really need to make a big effort to convince a reviewer that your method is interesting. Basically, n squared is the limit. It's the tolerance that people and kernel methods died more or less because of n squared. But n cube is really way beyond what is acceptable nowadays. So on the one hand, if you are someone in OR, in optimization, this is great. But if you want to apply this at a large scale, where you're going to compare probability distributions with tens of thousands of points, hundreds of thousands of points, this is not acceptable. It's not possible to actually play with this. So you definitely need to do something else. And let me just also say something that I think is maybe a bit of a problem with linear programming when we try to use it in machine learning, which is a bit something of the instability that you get out of as a byproduct of linear programming. So let me explain a bit what I mean by that. So people familiar with this know this under the idea of sensitivity of linear programs. How does the solution of a linear program change when you change the inputs? And remember, we are going to change a lot of the inputs of those Wasserstein distances because we want to minimize them, etc. So let's do a cartoon game. Imagine that I change a little bit my x or my y. Then what happens is typically this direction here will wiggle a little bit, will change a little bit, and sometimes, this never happens in practice, of course, because it has probability 0. It's a probability 0 event if you're playing with more or less continuous data. But sometimes you see that the direction will be orthogonal to a facet of this polytope, meaning that all of those points are solutions. But what happens a lot, though, is that you will jump from one solution to the other. So this is why, basically, the Wasserstein distance is not differentiable in its inputs if you consider the simple definition by Kantorovich. So you have something that's fairly big and costly to compute. So the Earth movers distances were fashionable, I told you, around 2000. People then were using histograms of dimension, let's say 100 or 200. And then at that moment, it was not so much of a pain to compute the Earth movers distance. But then when people started using SIFT or GIST or all those feature vectors that maybe were of dimension 4000, people thought, okay, it's impossible to compute MD on such big histograms. But then people hadn't really even understood, I think, at that time that there was also a problem with using this distance, which is essentially that it's very, very unstable. If you want to differentiate that distance, you will get something that's going to jump around. The gradients will jump around. So, and the last but not least, the code. Even though all of this is very well understood in theory of algorithms, who has tried to program a network flow solver? Is there anyone in the room that has programmed the simplex in his or her life? Okay. Okay, so it's a pretty daunting task. I mean, it's not easy. I mean, people have worked on those algorithms for decades and haven't managed to get something that's simple. The industrial solutions are essentially a mixture of a lot of heuristics and ways to initialize better your problem, etc. It's almost as bad as deep learning in a way, because we don't really understand why all of those tricks really work that better, especially when you start putting it integer programming and things like that. So here I'm just plotting the code for EMD point C in '98, something that has been used for a long time. So this is more or less as simple as you can, as simple as it can be. And already that just to compute this EMD, and that doesn't go beyond dimension, let's say 200, 300, is already 1,000 lines of code. Okay? So this doesn't sound like a very good candidate for learning in the GPU automatic differentiation toolbox era, right? Something that's extremely costly, something that's not differentiable, so you will not be able to automatically differentiate this algorithm, and something that's pretty unstable. And so the idea was, can we do something that's a bit more tailored to our needs in 2010, in this decade, instead of going always back to the formulation proposed by Kantorovich? So there's one approach which we have been using a lot recently, and it's very intuitive. It's just regularization. Whenever, I mean, there's so many jokes that are going on around regularization now in the community. I'm not going to do one, but it's just, if someone gives you an ill-posed problem, and this is what happens when you follow maybe the ideas that mathematicians have when they compare continuous densities, then you can start to regularize. Put ask more from your solution so that it is more stable, somewhat it is more robust. And that's exactly the idea here. What exactly was the problem with this P star? It's that it's wiggling around, it's jumping around, it takes a lot of effort to get there. Can we get something that's faster to obtain, that is more stable and more robust? And one solution is basically regularization with one regularizer that is, in this case, convex. Okay, we want it to be strongly convex. So this idea, this trick, has been around for a long time. This idea of regularization was proposed in the 60s by economists who themselves were already a bit frustrated with the math of optimal transport. They thought it was a bit too unstable. And so they said, okay, I'm going to add in something that's going to ask for more entropy of my solution. So what do I mean by entropy? Well, remember that this P matrix is a matrix which is a joint probability coupling. It has this, it sums to 1 because every row sum is equal to the first histogram, so it must sum to 1. So you can easily compute the entropy of this. And what is nice about the entropy is that if you are in the simplex, the entropy is 1 strongly concave. So if you remove the entropy times gamma, and gamma is a positive number, the regularization strength. So this becomes a strongly convex, what we call a gamma strongly convex problem in optimization. And what's the difference between a strongly convex and a linear problem? Well, you have unicity of solutions. Things are better behaved. You can say a lot more things as far as optimization goes. And now let me just try to give you a hint of what changes when you add this. Okay, I'm adding a regularizer that asks for more entropy. So here is the solution as gamma increases. When gamma is equal to 0, you get essentially the optimal transport solution. And when gamma goes to infinity, I will get back to what you get. So let me just make this a bit more clear. It's difficult to see it on the VGA screen. So here I've underlined what the solution, the optimal transport solution. So here imagine that you have a univariate distribution, another univariate distribution. So we know actually to compute this in closed form, but let's pretend we don't, and do the optimal transport problem, okay? So we're just going to solve. So this is discretized maybe on the grid of 100 values, 100. So my problem is of size 10,000. I am computing an optimal transport matrix of size 10,000. What I get is essentially this matrix, which is extremely sparse. Is that a surprise? That you get a sparse solution? No. When you do linear programming, if you have 10,000 variables and you only have 100 plus 100 constraints, which are the marginal constraints, then you will get a solution that only has up to the number of constraints, non-zero value. That's a fundamental linear programming result. So if you look at what this means, it says, well, if I were Kantorovich and this was my distribution of soldiers somewhere on the line and this is where I want them to end up, And here it's finely grained, so I have a lot of points, so it almost looks continuous. What it says is essentially, well, all of the soldiers that are here, you send them all here. And all of the soldiers that are here, you also send them there. So it almost looks like the Monge problem, okay? So the finer, the more the problem is fine-grained, the more you approach what is really a continuous distribution. It's no surprise that what you get is something that really looks like a deterministic mapping. You just say, oh, all the mass that's here goes there. Now, it might be counterintuitive, but when I add this entropy here, what I want is this distribution here to be more blurred, right? Has more entropy, to have more entropy. And so that's the complete opposite of what Monge wanted. Monge wanted some clarity of mind, which was, if I have mass at x, you bring it all at t of x. Kantorovich says, if I have mass at x, you're free to put it a bit around wherever you want. And we're saying, actually, you might spread it out a bit more. That would be great. If you could have me spread it out a bit more, that would help. And so the more you spread things out, and the more you ask entropy, in the end, what you get is, what's the most spread out thing that I can ever get that maps this transportation, this measure to this measure? And it's basically the one that we've been talking about earlier on, which is independent coupling. It's just the product of this times the product of this. If really the only thing you care about is entropy, well, the maximal entropy coupling of two marginals is basically the product of the marginals. So I would like you to understand that this is for me, this summarizes a lot of the lecture. By adding this entropy, we're basically going from almost what Monge wanted, which was computationally made possible by Kantorovich, to something that's very, very blind to the geometry of what's going on. And the only thing it does is just connect everyone with everyone. Okay, just spread out the mass proportionally everywhere. And what I would like to tell you is that, and I will see this later, this is MMD basically. The maximal mean discrepancy that Arthur was mentioning is the idea that everybody talks with everyone, and then we just sum up basically how far they are from each other. I don't know if you remember, you still have in mind the formulas that Arthur gave, but there were a lot of double integrals where I was basically summing everyone in x to everyone in y, and then taking this big sum. And this is what happens when you only focus, you're just saying, okay, I don't care, I want something that has maximal entropy. On the other hand, if gamma is very small, you're back to what Monge wanted. I want exactly to know where I should bring the mass from x to where. And this has a lot of nice mathematical properties, but this is a nightmare to compute in practice, in algorithmically. And one of the sale points of this lecture is to say, well, you can actually interpolate between the two at a computational price that's not too heavy. And I will explain why actually this is maybe 1 million times faster to get here than to get here. Okay, so this is for the big picture. Now, why is it that easier to compute this compared to this? Well, it's easier because it's just a result, I think, of optimization. We're turning this problem here into a strongly convex problem, and it's one problem for which there are very efficient algorithms, very simple algorithms, but that are very efficient, and that scale, and that can be used on GPU hardware. And so there's not that, if you do, there's two types of optimization people. It's either continuous or more discrete based or linear programming, for which you have a lot of conditional statements and you have a lot of pivot rules and things like that. The minute you add a bit of regularization, basically you're back to convex optimization by Boyd and Vandenberg, the standard toolbox. In this particular case, there's one thing that's actually appealing, which is if you write the first order conditions for this optimization problem, they're fairly straightforward. It's just the first time you take an optimization course, there might be an exercise to write the Lagrangian of this, take the derivative, and see what happens. So if I want to minimize this, subject to these two constraints, well, typically, I write first the objective. I will write the Lagrangian, which is the objective, plus a Lagrange multiplier for the first constraint. So it will be alpha transpose, the difference between the marginal of P and A, and beta transpose, the second Lagrange multiplier, P transpose 1 minus B. And then first order constraint is just simply, I want this to be 0. I want the gradient of this to be 0. What can I get out of this? So if you write this, the gradient of L with respect to to P. So if you write it element-wise, what you get is that you have this factorization. You get something that says basically Pij must be something like exponential of alpha I divided by gamma, exponential of beta j divided by gamma, and this value here in the middle that I already know because it's the distance between the points, the point I and j. And so what this gives you, I'm trying to summarize it in this result, it says, well, the solution of this problem must have the following. First order conditions tell me that it must be a factorized, it must have this factorized form. And it has a nice factorized form, which is, it has to be the diagonal of some vector, a diagonal matrix of some vector, a matrix K, which I will introduce next, and the diagonal of another vector. And you need to find those two vectors, u's and v's. And those vectors are non-negative because here you see this exponential. And what is this kernel, this K matrix? Well, I wrote it K because it's the exponential of minus the matrix of cost. So it's an element-wise exponential divided by gamma. So here you can see something appearing. It's like the reason why I call it a kernel is because often when you take a distance and you take exponential minus of the distance, you get an RBF type of kernel. And this is why here I write it a K, and you will see that it will play a role. So to summarize, my solution has this, must have this shape. Now the whole game is to find U and V. How can I do this? Well, I know something more about the solution. The solution may have this factorization, which is given to me by the first order condition, but it also satisfies the constraints. That's the second part of the first order conditions. And hence, I need to have a matrix which is diagonal UK, diagonal of V times 1 equals to A, the first marginal. Diagonal of V, K transpose, diagonal of U, so this is this matrix transpose, times 1 is equal to B. So we have two sets of equations that link U and V. And if you look at those equations, they are non-linear equations. Those are not, we can't solve them like this directly. But what we can surely do is try to play with them. So if you take the diagonal matrix times the vector of 1, what you get is actually the vector itself. That's not difficult to see. So we can replace those two diag V1, diag U1 by directly the vectors. Now if you take diagonal of a vector times one vector, you're doing the element-wise product of two vectors. So it's the same thing as doing U element-wise product KV. V element-wise product K transpose U. And you want all of this to be equal to A and V here, and B here. Now we might go a bit further and just make this a bit more clear. We're going to put this on the right side. So we have U is equal to A KV, V is equal to B K transpose U. So the whole point of this is to find two vectors, U and V, that satisfy these two equations. How hard is that? Well, there is certainly a very naive approach that one can take, and it's a fixed point iteration. If I want U and V to satisfy this, then let me just first ensure that U satisfies this, then V satisfies this, but by updating V, I'm breaking the first equation, so I'm going to do this over and over and over again. And that's called Sinkhorn's algorithm. So Sinkhorn, the name of Sinkhorn is playing a role in this optimal transport community now because of that algorithm. And so essentially, what you just do is you apply this update over and over and over again. So compare this approach to the approach that we were putting forward with linear programming, network flow solvers. It takes a lot of time to actually code a network flow solver and to improve it. Here, the only thing that you need to do is 3 lines of code. It's a while loop, and then it's 2 sets of operations. And those operations are actually very simple. It's element-wise division, and then matrix times the vector product. So the history of this algorithm is actually dates back to the 30s. It's not Sinkhorn who invented it. It was called the RAS method, IPFP method. There's several different names for this. But Sinkhorn was the first to prove that it converged, that the fixed point iteration was constructive, the iteration was constructive. And then there's been a lot of work on this algorithm to understand how fast it converges. So there's some interest recently in literature. So this was a NIPS paper in 2017. There's been new RIPS paper this year, but keep on trying to get better bounds on the convergence. But what I would like to try to underline to you is the fact that the main computational effort in this algorithm happens by multiplying this kernel matrix times a vector. Okay, that's n square if you want, or nm complexity. And I will show you later that this complexity can be brought down to n log linear complexity. So let me try to give you a cartoon of how this works. I have the two measures, mu and nu. They have weights a, b, and locations xi's, yj's. I will put the locations somewhere in this matrix of distances, and I take the element-wise exponential of that matrix, and I call it k. So what I just do is I start with a random vector v0 of the size of the second measure. I multiply k times this vector. I divide a by this, what I just got, and that gives me u. And then I do this over and over again. Okay, I alternate. So this is a very concrete visualization of this iteration. Why am I doing this? Well, I'm doing this to illustrate the fact that this is inherently easy to parallelize. That is, if I have several histograms that I want to compare simultaneously, it's very easy to do this iteration by just, so this is the result that I get, this is the actual value of the cost that I get, but let me just say that it's easy to imagine yourself in a world where you don't want to compute just the distance between two histograms, but you want to compute it between, let's say, 10,000 histograms, or 10,000 point clouds. Then in that case, what you would essentially do is stack vectors and just simply do it this way, right? So it's just a fixed matrix iteration instead of being a fixed point iteration. So this might be look very naive, but this was not possible with the linear programming perspective. If you had, let's say, 10,000 histograms to compare, pairs of histograms to compare in a linear programming world with the network simplex, then you have to run in parallel 10,000 times your little simplex algorithms. And that doesn't scale very well. This really scales, because the big difference is that instead of doing 10,000 matrix vector products independently, we just do a big tensor operation. And so as you can imagine, you get a lot of speedups. Now, maybe I've been a bit too greedy. Yeah. So this results date back to the first paper on the subject about 5 years ago. But basically what we were seeing at that time is that using GPUs, it was actually easy to scale up significantly compared to the network flow solvers. So we would get things that were maybe, let's say, 1 million times faster for relevant dimensions. Let me say, though, that I'm comparing oranges and apples, right? On the one hand, I can play with the linear programming solver that is off the shelf. It will compute an exact solution to my problem, whereas here I'm comparing it to something that's regularized, where I'm not really aiming for the same point. Remember the picture where I had P star? I'm aiming for something that's inside, so maybe it doesn't make so much sense to compare them. But still, if in applications you are as fine as with this smoother solution than with the real one, then it makes sense it makes sense when someone tells you that you get there 1 million times faster. Now, let me just try to illustrate this, for instance, on another example, which is 2 MNIST digits. Let's say I want to compute optimal transport between two shapes. So here I have a probability distribution and another probability distribution. Just to be clear, this image basically in this setting represents a probability distribution supported on this area and 0 elsewhere. Okay, I have color bar. Maybe each intensity of each cell is between, let's say, 0 and 0.015. So if you sum up all of those intensities, you get 1. And if I sum up all of those intensities, I get 1. So imagine I want to compute optimal transport distance between those two, but with this regularized approach. So what I would do is I would initialize things with a noise. The V vector has the same size as the histogram, the second histogram. So here everybody has the same size, so there's no n equals m. And then what I would do is basically apply this kernel. So you remember the kernel matrix is of size n times m. Okay, so just to set dimensions right, here this is 28 by 28, or let's say it's 20 by 20 to simplify the argument. It's 400. Okay, this is 400 cells. The kernel that I'm applying is 400 times 400. So it's already quite a big matrix. And then I'm applying it to this matrix of size 20 times 20, 400, but seen as a vector. What happens, though, in this case is that if you actually look at just the formula, what the kernel I'm applying is only a Gaussian convolution. It's only a Gaussian blur that I'm applying to this image here. So in this case, we get something that's much faster than actually. We don't need to apply this Gaussian convolution by applying this linear operator of size 400 times 400. We just apply a Gaussian blur, and then we just divide this by this, and it gives us this. And then next time we apply the Gaussian blur to U1, we divide this by this, and we get this. And then we do this over and over again, and then we can keep track of this big, if you want to. If you want to instantiate this big optimal transport matrix, it would be a matrix of size 400 times 400. That's not easy to visualize, of course, here, because the pixels have the ordering by columns. But still, you can see what the synchron algorithm looks like. So very quickly, the synchron algorithm starts producing, and people that use it for the first time think there's something wrong. My U's and V's here, maybe we won't see it very well, but this is already 10 to the power 10. And then when I keep on applying those synchron iterations, it just makes them bigger and bigger. So this is already 10 power 10. This is probably 10 to the power 30 or something like that. So you start seeing this weird thing, which is, if I look at U and V, they don't seem to be right? They have huge values. Some of the points have huge values, and the others have very small values, relatively. So let's do something very simple, which is let's plot this in log space. Okay, I'm going to plot those two U's and V's in log space. And then what appears here is something interesting, which is that I didn't elaborate too much on the dual optimal transport problem, but let me just try to give you an intuition of what this shows. So I'm just going to do a few iterations more of the algorithm. Here what I'm actually also measuring is how far I am to the actual marginals that I want. This is a way to monitor the convergence. And so this is, let's say, 0.44. I'm decreasing how far I am from the real solution. Now, let me just stop at iteration 20. I think 10. Sorry, I think it's maybe I need to be a bit closer. So here, those two U's and V's, the log of those two U's and V's, have a very nice interpretation. What essentially they say is, among those points that are in this measure and those points that are in this measures, which ones are the ones that really annoy me, that basically increase the Wasserstein distance between these two distances? And those that really annoy me will be visible with high values. And so as you can see, well, it's pretty clear that any point that's in this area, if I want to transport this to this, well, it seems that those points here don't really cost so much because they already appear somewhere in this area. And even those points here, I might find a way to make them go down a bit or up here. The point, the areas, the weights, if you want, that really are costly are those ones, because there's no way I will easily transport them to this one. And if you look at the one here, well, actually it's the one that are on both ends, because all those that are here relatively are easy to somewhat distribute, but those that are here do not appear in this 7, and those that are here do not appear here. So if you actually look a bit into duality, what you can see, and this plays a role also in this Wasserstein-Gahn paper, is that the dual weights that you get out of the Wasserstein, the competition Wasserstein distance, basically tell you what is really that you want to change to reduce the Wasserstein distance. And so if I wanted to, for instance, make this 7 look closer to a 1 in Wasserstein distance, the first thing that I would probably do is start focusing on those pixels here. And if I wanted the 1 to look more like a 7, the first thing I would do is basically start moving those pixels here. So this is, I hope, something that illustrates the fact that both you get as a byproduct of this Wasserstein distance computation a gradient, and especially when it is this smooth formulation, and that for some regular domains like this, very often this multiplication by a kernel is actually much cheaper than the quadratic cost up front that you would have to pay naively. So let me just say, for those of you who are experts in optimization, that I've been talking about the Synchron algorithm as if it was something that Synchron invented, it's a magic thing, and it seems to live alone in the galaxy of optimization, but it's not really the case. You can very easily interpret this algorithm as a block coordinate ascent in the dual of this regularized optimal transport problem. So the regularized optimal transport problem is this max, is the minimum of this on the matrices. If you actually compute the dual, the convex dual of this problem, what you get is this type of problem, and then what you get is this problem. And if you actually do a block coordinate ascent on the dual, what you essentially recover is Synchron. So let me just try to show you this. So imagine you have this problem. You want to maximize on alpha and beta, two vectors, the dot product of alpha with A and the dot product of beta with B, minus this formula. So trust me, this is the dual. So it corresponds to the previous problem. The problem here is not constrained, unlike the previous case where we had this constraint that P had to have the right marginals. Well, what you can do in this case is block coordinate optimization. What is block coordinate optimization? Well, it's essentially I'm just going to freeze one of the two variables, beta or alpha, and I'm going to do my best to optimize with respect to the one that I'm not freezing. And so if you actually compute the gradient of this energy with respect to only alpha, you get this thing. So it may not be obvious, but it's basic computations. And if you compute the gradient of this energy with respect to beta, what you get is this thing. Now, block coordinate, ascent or descent here, is essentially I'm just trying to choose alpha such that the gradient here is cancelled. I might do this iteratively, or I might get a closed form solution. And in this case, actually, it's easy to get a closed form solution. If you choose alpha, which is this quantity, you can very easily see that this is 0. And if you choose beta, that is this quantity, then you get that this is 0. So all in all, if you were to make a parallel between Synchron and this naive approach here, block coordinate on ascent, well, it's easy that if you define u as exponential alpha divided by gamma and v as exponential beta divided by gamma, well, doing this block coordinate ascent update is the same thing as doing the Synchron updates. Okay, so it's just a way of demystifying this Synchron thing. Now, I think I'm going to skip this because this is a bit, I leave it in the slides, but this is a bit more technical. It's essentially how this can be used in a continuous setting, and this is more of interest when you actually start playing with GANs and things like that, when you have to sample and do stochastic optimization. Let me just now explain a bit more about this, the proximity with this, with the MMD. The discrepancy. So I hope you're all now familiar with this picture. We have two measures. We have a matrix which is defined by the two sets of points. We have a polytope which is defined by the two histograms. If I do Wasserstein optimization, optimal transport, I look for the point here that has the smallest possible dot product, and this is P star. Now, if you remember, what I'm advocating is let's just look not so much at P star, but let's look at P gamma, okay, the value of my regularized optimal transport plan, the one that I get after an infinite or a very large number of Synchron iterations. And then if you remember, what happens when gamma is infinite, when it's very, very large? Well, as gamma becomes larger, you get closer and closer to this independent coupling. And when gamma is infinity, you get the independent coupling. So here in this case, an independent coupling is essentially just A times B transpose. Okay, it's just the outer product of the two marginals. So you can see that this regularization helps you interpolate between two things, which is either the product of the independent coupling or the P star, the one that is actually very hard to compute. And getting here is okay, not too complicated computationally. Now, what you can see is that if you actually look at those three values, only this one is 0 if mu is equal to nu. Why is that? Because if you say that x is equal to y and the weights A are equal to the weights P, then basically the P star is just a matrix of those weights. Meaning basically, okay, if you want just to compare this measure with this measure, then you transport this point to this point, the cost is 0, this point to this point, the cost is 0, etc., etc. So if you compare two measures which are the same, you get something that is 0. Now for this regularized approach and for this naive coupling, it's not the case. So what you need to do is do some form of centering, if you want. You want to do some kind of normalization where you subtract by what you would get if you were comparing the measure with itself and the measure with itself. And I think that maybe this is still fresh in your memory. In MMD, we need to do that, right? We want to compare one measure to the other, and then we need to subtract what we get with the measure itself and the other measure with itself. So to give a visual explanation, we have two clouds of points. All the points communicate with each other and see how far they are from each other. But we have to remove how far each points in the first cloud are from each other and each point in the second cloud are from each other to get something that's 0 if you're comparing the same point cloud with itself. And then here in the regularized Wasserstein that I proposed, we can also do this trick. So there is an interesting amount of work which has been done recently on this object. Is it really, so does it behave like a distance or not? Because I'm just defining it. It's 0 when mu is equal to nu, but there's nothing else that I can say outright. Well, it turns out that this thing also has very nice properties. So let me just try to tell you how we can compare them. Oops, I hope no. So if I were to give you two divergences between probability distributions, it's very hard to say that one is better than the other, right? It's not obvious to say, oh, this one is, MMD is better than F divergences, or Wasserstein is better than the Kullback library, etc. They have a lot of properties. There are lots of reasons. Each of them has some argument that someone is trying to sell you, to tell you this is good because. I can think of two arguments which actually are quite important in machine learning, make a lot of sense in machine learning, maybe more than in other communities. And it's the idea that you want to have something that's easy to compute, fast to compute, and the other is more like a statistical property. And it's usually called the sample complexity. So let me be more precise, and I think Arthur also mentioned this a lot. Imagine that I have samples that come from a measure mu and samples that come from a measure nu. That's the problem we have, right, in statistics and data science, is we never have access to the true measures. Well, imagine I want to compare mu hat n and nu hat m. Okay? Or I should probably have been less ambitious, just n. Let's say that m is equal to n to make things a bit simpler. So there's two things that you can ask. Is how, if I come up with a divergence or a distance, how costly is it to compare these two things? So if I have n points, is it going to take me linear time in n, quadratic time in n, cubic time in n? So as we've seen, if you just take the Wasserstein distance, it's cubic. If you take the MMD, it's essentially squared, and that's not a bound. It's exactly the effort that you need to make. You can make that a bit faster, and I don't know if Arthur mentioned this, but for in some settings, this can be a bit faster. But it's essentially quadratic. Everybody talks to everybody. And if you take this regularized approach, it's quadratic, but with more effort than the MMD. You need to, each iteration of Sinkhorn is a quadratic effort, and we have a lot of theory on it goes fast enough so that you can see that it doesn't really grow with the number of points beyond that. Then there's the other thing, which is that statistical properties. So if you've read a bit the literature recently, it's all about this idea that if, when you compare two samples, you are very far from what you would get by comparing the two densities, if you had the densities, then this divergence is maybe not that useful. Meaning there is a limit, statistical limit to what you're doing. You might be defining a very exciting divergence, but if it somewhat is very hard to estimate with n points, then it may be not doing the right job. And so those two aspects, we can actually somewhat compare those divergences based on those two aspects. So the first thing is complexity of computation. So MMD is, as I said earlier, just quadratic, and complexity, statistical sample complexity is 1 over square root of n. I think Arthur mentioned this. Wasserstein is very costly. So here I gave the actual bound in terms of if you have n and m. But what's horrible, and I didn't really mention this, this was a bit an elephant in the room. Think about what you're doing when you're doing Wasserstein. Imagine you have 2 densities, you sample points, and then you're going to work really, really hard to find the best possible way to match them. And you work so much that you actually have cubic time trying to match them. And if you have a ML background, well, you know that working too hard on samples is somewhat overfitting. And this is exactly what happens. What happens is that because you're overfitting a lot and you're really trying hard to go and compute the optimal coupling and the distance, what you're doing is you're working so much that you're far from what you would get if you really had access to the probability distributions themselves. You never have access to that, right? But in theory, there are ways we can compute such bounds. And so if you are in dimension D and you're using Wasserstein 2, the square Euclidean distance, there's lots of results. I'm simplifying the argument here, but it's of the order of 1 over n power 1 over d. So it's a complete disaster. So if you're a lot of the pictures that I showed you were in dimension 2 or 3, so in those cases more or less okay. But imagine you're in dimension, let's say, 10. Well, the way you will be able to approximate this using samples will be bounded by 1 to the power n over 1 over 10. So that's just very bad. And what we showed recently is that so sinkhorn, this family of divergences have a lot of nice things for them. So first, there are convex in mu and nu, and those are recent results that one of the authors of this paper is Amari, Shunichi Amari. So this is very nice because he's very interested in Wasserstein distances. He's 82 right now, but still an amazing researcher, and so he has been working on this. And then we also showed that there is a nice statistical sample complexity result, which is that what we get is we get something that looks a lot like MMD and not at all like Wasserstein distances, in the sense that we have a sample complexity in 1 over square root of n. But, and this is the caveat, there must be one, there is a constant that pops up here that depends on the regularization. So basically, if you are not regularizing, if gamma is quite big, then this constant will play a role, but it might basically, the sample complexity will be 1 over square root of n. If gamma is very small, so you look a lot more like this, then this constant explodes, and this doesn't really count. So we get something that's quite coherent with what we would have expected, except that we have this result that it's now in 1 square root of n, so just like MMD. So we have a few nice arguments. So now let me just try to talk about something else. So I hope I have convinced you of a few things. Basically, when you have 2 clouds of points like this, we can try to compute something that looks like the Wasserstein distance, maybe regularized. If we want to be very lazy, we compute MMD. We just take a very flat sum over the dependent coupling. If we want to work a bit harder, we do a bit of sinkhorn iterations. If we want to really work hard, but in practice we rarely want to do that because of those statistical limitations, then we can actually let sinkhorn gamma go to 0, or solve the linear program, which is what people would have done a few decades ago. Now, one question that I haven't raised so far is about differentiability. I told you I'm going to compute this. Computing something and being able to give you the gradient of something is a bit different. If the computation is easy, then it's really easy to get the gradient. But if the computation is hard, and this is what happens in linear programming, it's not so easy to get it. So let me just help you visualize what I mean by a gradient in this case. So for me, a gradient in this case would be something like this. It would be what happens if I change a little bit the weights. Okay, what is the best way? Oh, the animation. Okay, so there is no movie. Okay, that's why. I guess this works. Okay, so what happens if I change a little bit the weights? What is the best way to change the weights to make this closer to this? So typically you would imagine that it would be increasing this weight and this weight maybe, or this weight, and decreasing those weights here. So I want to know that. what happens if I want to change locations? So what is the best way? What would be the Wasserstein distance if I just change a little bit locations? And so those two questions of differentiability, of course, are connected to how we will try to approximate the Wasserstein distance. So let me just skip those two slides, because those are works that are of a very orthodox convex optimization flavor. And I will go straight to what actually people like to do now, which is automatic differentiation. So why is this synchron alternative to, or regularized alternative, appealing compared to the traditional linear programming approach? Well, it's because if you followed what I've said so far, essentially what I told you, or what I could tell a programmer is, okay, I'm going to compare 2-point clouds with different weights. I have this algorithm that's really simple. It's just a while loop with two updates. And it goes like this. You start with something random or ones. You apply this, let's say 50 times. You just write it hard code 50 times. And then after 50 iterations, you look at what you get. And you compute the price of what you get. This is the cost of what you get. And then let's call this the algorithmic Wasserstein distance. Okay? It's not the real one, but it kind of approximates it pretty well. Now, if I want to backprop through this, it's trivial, right? Every iteration in this algorithm was a simple matrix vector product or an inversion. And so what this gives you is some kind of black box that can mimic the Wasserstein distance, but which is, you can backpropagate to it. So let me just give a neural network feeling to this statement. What it just does is takes as inputs 4 things: the weights and locations. Maybe you might consider uniform weights for that matter. Maybe you don't want to change this. But you have weights, you have points, sorry. You stack them in some distance matrix. You take the element-wise exponential of minus this distance matrix or this cost matrix. It doesn't need to be a distance. And then you will do this stacked, basically, neural network where at each iteration you could see the nonlinearity as just simply A divided by what you just got. And of course, A appears here. It appears in the nonlinearity. X and Y's appear in the K, but you can backpropagate through this very easily. And so it's very easy to basically incorporate the Wasserstein loss in any neural network architecture or pipeline, or even just doesn't need to be a neural network, but just to get something that you can very easily differentiate and backpropagate. And this was done recently in a couple of papers since 2016. If you go a bit back, Richard Zemmel and Ryan Adams had the idea of backpropagating through synchronous algorithm for assignments around 2011. So this closes more or less the computations part. So I hope I haven't sent too many mixed signals, but probably this is the only thing that you might want to remember in the end, if you're not interested in optimal transport theory, is if you want to use the Wasserstein distance for any purpose, suppose you output a distribution and you want it to be closer to some other distribution, and you want to backpropagate an error, you don't want to use Kullback-Leibler, fine, you just use this kind of stacked. And so just as MMD GANs was a possible way to train GANs, well, a synchron GAN or an optimal transport GAN would be this, but except of doing just one iteration of MMD here, you would actually compute, you would run synchron a few times and then backpropagate to it. Any questions before I go to some applications? Oh, I'm running out of time. Badly, right? 5 minutes, yeah. So, sorry, no applications today. Yes. You mean, can I do this if the distributions are changing? You mean dynamically, or in what sense? Yes. So the distribution is approximated by parameter theta. Well, as long as you can backprop to the map that takes a parameter theta to the distribution itself, you can backprop to the whole thing in the end, right? You will just add a Wasserstein distance of this distance to, and this is what people have been doing in GANs as well. So there is, you can, if you can backprop through the parameters of the measure itself, so it might be locations or it might be weights, then you can, and you have a mapping that gives you, that goes from the parameter to those locations or weights, then you can backprop through the whole thing. So this, in a Wasserstein GAN, this is what people would. So there's an extra layer of in your network if you want. Theta, what the measure looks like, and then what the backprop through that. So I don't have so much time for applications, but I wanted to be take my time to explain the algorithms. Let me just say that very quickly. So about 20 years ago, what people were using Wasserstein for was essentially retrieval. They were only interested in computing the distance. So the most well-known example of this is the Earth mover's distance. So you would represent an image as a histogram of colors, compute optimal transfer between the two, and call this the EMD. More recently, maybe you're familiar with this, but this is an area where a lot of optimal transport is also being used recently, is the idea of comparing clouds of points, which are actually clouds of words, in word embedding space. So this was, there was some work following Kuzner's work in 2015. Suppose I have one sentence, another sentence, I can see that as a cloud of words in the space of word embeddings, and then why not use optimal transport on this? So this has gained a lot of popularity. Now, these two applications are essentially give me two distributions, I will tell you how far they are from each other. What I was telling you is that in many applications, what we want to do is a bit more than that. We don't want to just know how far two things are. We want to minimize how far two things are subject to a parameter. And so the idea is this, that you want to Wassersteinize things. So instead of using Kullback-Leibler, you would typically try to inject a Wasserstein distance if it makes sense for your problem. I'm not saying it's a panacea and that it always works, but for a few problems we've seen that it does bring some edge. So there are a lot of problems that, I mean, there's one problem at least that you all know, which you maybe didn't know was a Wasserstein problem, and that problem is k-means, the Lloyd's algorithm. So when you think about k-means, you have a big data set and you want to find k anchor points, or k clusters that represent well the data set. Well, the fact that the way this is well represented is actually in Wasserstein sense. What you can formulate the k-means problem is simply as, you give me a probability distribution, then the quantization problem in general, I want to find a measure supported by k atoms, so it's a budget of k atoms, and I want it to be closed in Wasserstein sense. Then there's other things, but this is more from pure math, so let me just skip this. So average was this idea that I want to find something that's in between the two distributions. The Wasserstein barycenter is the generalization of this idea. And then when we found this Sinkhorn algorithm that it was running well for applications to compute the distance, we also understood that it was nice to differentiate it. And so the way you would compute the barycenter, of course, is what is the measure that is the closest on average to all the other ones, right? So you want something that's not too far from all of this. There's no closed form from this. There's one when you are in Euclidean space, but when you are in the general metric space, there's no closed form. So you need to optimize this. So you want to minimize the sum of Wasserstein terms, so we need to have an algorithm to do that. And one simple way is to either rely on closed forms when you can in the univariate case. So in univariate case, I hope you remember, it's all about quantile functions. But when you are in more general case, you can ask yourself, how can I do this? So here it's an example where we averaged a few measures. Exactly, there is actually an exact solution, but only when the number of points is very small. So let me just skip this. Let me just go to the illustrations. So the first time we actually were interested in those barycenters and tried to find to see, just try to get a feel of what it was doing. We tried with this experiment where each image here is a probability distribution supported on 3 ellipsoids, and we're asking what is the mean, the Wasserstein mean of those things. And then, of course, if you compute the Euclidean mean, sorry, you get this big blob, whereas if you compute the Wasserstein mean, for some reason, you have those 3 circles, concentric circles that appear. And here I'm not using any information on what the images are. The thing that I'm using is the Wasserstein geometry. So I have a few more slides, but I think I'm just going to stop here. Maybe let me see if I have. No, I think I may just directly jump to the conclusion. Up. So with this lectures, I hope I've tried to convey something that's basically the Wasserstein distance is this nice geometry. Optimal transport distance brings something new to compared to other divergences. And what essentially it's using is the knowledge of some geometric structure on your observations. So since you're building on some knowledge that someone gave you, and you're optimizing on that knowledge, if that knowledge is bad, you might make bigger mistakes, right? So you have to be careful that all of this is useful when somewhat you think the knowledge that you have, the geometric knowledge you have is actually a good one. Now the good news is that before those kind of tools were not accessible to us, people more in applied math and machine learning because of computational issues. And now we've been working out a bit solutions for that, and they work. And what's much better is that they work with a modern paradigm of very parallel computations with GPUs, automatic differentiation when you don't want to compute a gradient again in your lifetime. And it seems to be giving a lot of nice results in applications, as varied as NLP, graphics, of course, where everything seems to fit this optimal transport paradigm, but also generative models. Now, there's a lot of work to do still because we don't understand very well those divergences for which we optimize. So think about the difference between F divergences or MMD and this. Well, here, when we compute a distance, we're actually working a bit. We're trying to find a way to match things. In the F divergence world, I'm taking a blind, I'm not putting any bet on anything. I'm just integrating the difference or the F function of the ratio of the two distributions. And because you're not working, it's a paradox, but in statistics it's well understood. Because you're not trying hard, you're more robust. Because you're blind, basically you don't make that many mistakes. It's a bit weird to say that. Whereas if you have access to information and you work a lot on top of that, you overfit, and then that makes you maybe a bit far from the true divergence that you will have between the two distributions. So computationally, there's lots of possibilities. In the application world, I think there's lots of things to do as well. So thank you very much.